Since the beginning, since 1990, the focus was not on the machines, so we have never, let's say, produced machines to sell them, but we have been focusing on software technologies. Software technologies to make the 3D printing process as fast, accurate, and reliable as possible. Also, software technologies that push more and more markets within the 3D printing field, such as the medical market and so on. 26 years later, this is what we are doing right now.
Everything starts with an idea. It gives us a hint of what could be. It makes us invent the new and improve what is already there. An idea can change the world. So we better bring a good one to life the best way we can. That is why we have created one of the most advanced factories in the world. With best-in-class machines, powered by best-in-class software. With certified post-processing and quality control, and the people that breathe manufacturing. To honor those great ideas, to shape them, to turn them into great products, again and again and again. We're in the car you're driving, and in the plane you take. We're here. And here, and also here. For over 25 years, we've been around, bringing additive manufacturing to where it is today, and we keep pushing the boundaries to ensure that every idea we materialize delivers what it promises. That is our pledge.
So 26 years later, we have become a global company, let's say a global leader in 3D printing and medical 3D printing. We have around 16 offices worldwide, and we have the largest group of software developers working on certified medical solutions. Every day we print around 2,000 parts, and the treatment of 60,000 patients every year is facilitated by 3D printing technologies. So the mission of Materialize within the medical unit is to take patient-specific healthcare to new heights and basically create a better and healthier world. So I'm going to present you some case study to make it a little bit more tangible. This is David Singer. David Singer is working at the MIT Media Lab in Cambridge, and he's living in Sierra Leone, or was living in Sierra Leone. And in 2002, the civil war ended in Sierra Leone. Due to the war, a lot of people lost a limb and were wearing artificial limbs. But unfortunately, those artificial limbs didn't really fit really well because they were not patient-specifically designed, and therefore they were not worn. Of course, this limits the level of independence of those people, and therefore David Singer decided to devote his PhD study on the design of patient-specific prosthetic sockets. So what has David Singer done? He has taken CT images. He used them to reconstruct the bones and the muscle, but also to get a good idea about the positioning of the fat and the bones surrounding the lost limb. In that way, he could make a prosthetic socket of different materials. Softer materials where there's a connection between the prosthetic socket and the bone to make sure that the connection between the bone and the prosthetic socket doesn't hurt. And more stiff, rigid materials in the places where there's a connection between the fat tissue and the prosthetic socket. Afterwards, he has made a design, and then he created a mesh and exported to an FEA solver for finite element analysis. Based on that analysis, he could check how the prosthetic socket would react under different loading conditions. Eventually, the prosthetic socket was 3D printed with a Phonics 500 printer. It's a printer well known for being capable of printing different materials and different colors at the same time. So this is a really good example of how 3D printing technologies can impact the life of individual people. This is another case of a 17-year-old patient who had a tumor and for which a calcinectomy needed to be performed. When designing calcaneal implant, it's important to take into account weight considerations, but also mechanical properties. To address those considerations, the medical team at the MIT University in Melbourne decided to make a calcaneal implant in a porous structure. So what they have done, they have designed the implant They have added porous structure to it, performed a finite element analysis to check how the implant would react under certain conditions and so on. And based on that input, they have optimized the lattice structure. The advantage of working with the lattice structure in this case was that they have been able to reduce the weight of the calcium implant with 65%. Furthermore, they have been able to restore the load carrying capacity of the original bone by 85%, and the compressive stiffness of the calcaneum implant was statistically indistinguishable from the original bone, which is really important. So why porous design is quite popular right now, not only in a lot of fields, cranioplasty, spinal cage, and so on. So, but why is porous implants important? First reason is that porous designs are inspired by nature. So, for example, the inside of a femur is not solid; it has a porous structure to be able to cope with the daily forces that are put onto it. And I mean, a porous implant basically mimics those mechanical properties, but at the same time allowing a weight reduction. Another reason why you should work with porous implants is that it allows bone ingrowth. So bone cells will gradually merge within the implant, creating a better fixation between your bone and the implant. A final reason, and often not known, is that porous implants have better thermal conductive properties. So for example, when you're working on a cranial plate and you have just a solid model, then the cranial plate might shrink or expand under certain weather conditions. For example, when it's hot or cold, and shrinking or expanding an implant hurts the patient. It's also very important that you take into account the porous design within the design, so that you do not, first of all, print the implant and then add a porous layer on it, because you don't have that much of control on that layer. You will create a non-uniform thickness, and the thickness is usually not enough to really generate bone ingrowth. Furthermore, usually when you're working with a recoating system, the adherence between the implant and the porous layer is not very good. This is a cardiovascular case by the King Faisal Specialist Hospital in Saudi Arabia. It's done by Dr. Al-Mufa. So this is a case of an 18-year-old pathology of the Farad patient who underwent some surgical procedures earlier in life and was presented with a pulmonary valve insufficiency. In this case, the patient would be cured with working with a TAVI valve, which would be expanded in the pulmonary valve by using a balloon on the tear. But the problem in this case was that the medical team was not really certain about the device fit. So they wanted to test it pre-operatively whether or not the device would fit the patient. So what they have done in this case, they have sent their MRI images to materialize to us, and we have designed a few rigid models and a few flexible models for them. And that allows the surgeon to pre-operatively measure how the device will be. And this is visible in the next video. So they take measurements now.
All the steps that we've done this morning.
So that's a rigid and a flexible model we've designed. And now they will inflate the balloon and they will check the device fit.
Meant for this meant to wax. And here you see what we got when we get the smugging. And you see the smugging that we have produced with the same volume, and you see the 9 meter here. And this gave us really, doing it on patient, takes us a short in the procedure a lot.
So what is really important is the last sentence. They were able to shorten the procedure. And by being able to shorten the procedure, we are also able to reduce the recovery time of the patient. But what is important as well is that it gave the medical team a lot of confidence in the procedure. So they were already quite confident before the operation that it would be a success. This is another cardiovascular case from the Morgan Stanley Children's Hospital in the USA. So this was a fetus who was diagnosed with a congenital heart disease. It was a double right ventricle. So they took ultrasound images, but the quality was not enough to really plan the surgery. So the 3D dimensional relationship between the different anatomical structures was not clear enough on the ultrasound images to really plan the surgery. So they have waited until the baby was born. They took low-dose CT images. They generated a model. You see the heart model there. And that allowed the surgeons to really see what was going on. And the decide on the most optimal surgical procedure, which surgical technique should be used, and so on. And this allowed the medical team to treat this baby in one surgery only, while it usually takes a lengthy cycle of surgeries to be able to cure the disease. And every operation, of course, can be fatal. This surgeon who has performed the surgery mentioned that he would never use or never perform any surgery anymore without holding a model in his heart and his hand. This is another interesting case. It's about conjoined twins. So these twins were conjoined until they were 10 months old. They were conjoined at the chest and the abdomen, including the chest wall, the lungs, the livers, the kidneys, the pelvis, and so on. It took 1 year to plan the surgery. It took 26 surgeons to perform the surgery, 26 surgeons from 13 different disciplines. And it took the surgery took 30 hours. So one way to prepare for the surgery is by producing a 3D model. So what they have done, they have basically sent us color-coded visual images of the patient's anatomies, so the twins' anatomies. And based on that, we have developed a 3D model, which is this one. And this allowed them to decide which organs should be allocated to which baby. Furthermore, the model also allowed them to make the right cuts. For your information, the model was made in 6 days, the radiology imaging took 3 days, and the actual printing, which was done by a company in Dallas in the US, was also done in 3 days. A last case study I want to present is from a commercial company. DGO is a well-known medical device company. And DGO wanted to launch a new hip stem. And everything went quite well until pre-market validation. So they had 30 cases, but 8 femur fractures occurred. It was basically a hip stem called the taper film, and it was a less invasive hip stem, which closely matches the anatomy of the patient. So everything went well until the pre-market validation. 8 fractures and 30 cases, and this was a big issue because the surgeons didn't want to work anymore with the new hip stem, and they already announced that they will launch the product on a certain date. So basically the reputation of DGO was also at stake. Then they needed to find a solution, a quick solution, an effective solution that would help them reach the target. Then they heard about population-driven design. So population-driven design is basically calculating an average femur in this case and some variation models. To make it simplified, I'm wearing a t-shirt which is large. You might wear an extra large, a small or medium or whatever. That's the same with implants, but it's a little bit simplified. So in this case, they took a database of femurs. They calculated an average femur and some statistical variation models. Based on that, they virtually fitted the original hip stem into the average femur and variation models, and they found out that the femur was too wide at certain locations, causing stress at the femur. So stress caused the femur fracture. They slightly adjusted the hip stem, and then it turned out that there were 0 fractures in 60 cases. We are already at 91, if I'm not mistaken, and there was 1 fracture only. So this really shows how 3D printing technologies, population-driven design can also impact commercial companies. Because in this case, DGO already ordered a stock or produced a stock worth $500,000 to be ready for the market launch. So that's my presentation.